Hello guys, today I want to take you review two recent papers from Nature Communism. They are all about neuromorphic photonics computing, and yeah, they both have some novelties. But after reading those two papers, I would like to say I don't think this field has any future. Yeah, this is a video purely about sharing feelings, and I won't go into too much detail about these two papers. So let's first introduce what is neuromorphic photonics computing. Let's use this graph as an example. So here what we see is a waveguide, right? So typically you have a waveguide, and you can input several wavelengths, like let's say several wavelengths light, like lambda 1, lambda 2, lambda 3, and you can have so many of lambda, and each wavelength's intensity can be different. So all of the intensity forms a vector. When the light passes through the waveguide, you can let it pass several ring resonators. Ring resonators use resonance to tune the intensity of a specific lambda. Let's say this resonator only can tune the intensity of lambda 1. So how it tune the intensity of lambda 1, you can just imagine it as multiply a weight on it. And this ring resonator only works on lambda 1, and this resonator only works on lambda 2, and this resonator for lambda 3, so on and so forth, lambda 4. Yeah. So obviously what you will get finally at the output here is a linear combination of all wavelengths intensity times their individual weight. So output O will be I1 times weight 1 plus I2 plus weight 2. Yeah, if you are familiar with neural network, then it's a single neuron in the output fully connected layer, right? So neuromorphic photonics computing is just trying to make this as many as possible. So they want so many ring resonators in parallel, so the dimension of the input vector can be large, and and this will enrich their story, saying like it can work on modern AI neural network structure, like high dimensional matrix vector multiplication, and they'll claim this thing will be useful. But things it's not useful at all. About this paper, so what's its novelty? Its novelty is reframe the original structure, which is called spam DAC, into the new structure they have. So they will save a lot of digital to analog converters. Yeah, it looks familiar, right? I would say it's an impressive work, because originally you use one DAC to control one micro resonators, and you will waste a lot of DAC. But if you reframe it into a memory-like network like this, then so many DACs are saved, and smartly you use let's say, well, I don't know what exactly this is, but let's say using a MOSFET to control the charge and discharge of the memory here, and it will, here's a capacitor, so you charge the capacitor and you tune the weight of each of the ring resonator, and this will form a programmable, fully connected layer, right? This will form a programmable, fully connected layer, and you can use it to do something. Why I say something? Because optical things are pretty lossy. That means light pass through the weight, they will lose a lot of energy, and that's the huge limitation of this kind of optical neural computing. So you can imagine what's the final application of this paper. They say they use this structure to in situ training an MNIST dataset. That's the best they can do. What does the in situ training mean? The in situ training is model-free training. Why model-free? I'll explain it more. So let's say measurement-based training is what they mean here with in situ training, because optics people likes to invent some rocky words. So but actually in computer science it's just some perturbation-based stochastic gradient descent. It's nothing fancy, but because all of the gradient descent is based on your measurement. Why you have to use your measurement? Because the system is too noisy and so noisy that you can't have any models for this whole thing. It's called model free, so they choose in situ training. The big advantage is model free based on your measurement and make things work. But even if it works, the bad thing it can do is to work on MNIST dataset, right? So you can't build it larger. You can't have so much. You can't have too much microresonator arrays. So that's the limitation of this work. But I would say it's pretty impressive. But it's because it integrates so well into the digital memories and make it highly low latency and programmable. This is a huge advantage. But why don't you just use digital memories rather than you can directly use digital memories and digital weight, so you don't need to bother with optics. You don't need to have so many energies lost. That's my point. So I would say, yeah, it's impressive, but won't work on some huge matrix multiplexer application. So that's the first paper I'm gonna take you to review. Yeah, but the second paper is still about neural computing, and it claims that it can have a huge dimension vector matrix multiplexation, because they integrated time multiplexation into this paper. But how do they do that? They integrate the time multiplexing, so they still have the same microresonator arrays. They didn't make the resonator arrays larger. So they rather enlarge the time scope and try to do more multiplexing in time domain. So this paper claims they can, by using the heater effect, they can have so many weights added. They can have a huge linear combination of the input weight. So what's the dimension of your input vector? They have a dimension like this. Total dimension is the time dimension of the time times dimension of the lambda. Yeah, and finally they use time domain heating effect to aggregate all of the lambda and times or intensity and weight, and got a super large linear combination. I would say their design is smart but trivial. It's people have been spending their wisdom onto this trivial design, but it doesn't turn out to be simple and neat. It just doesn't look quite good. So I mean, they still use the micro resonator, but they divide their wavelengths. They divide their resonant wavelengths into two parts. So the first part is absorptive wavelengths. The second part is non-absorptive wavelengths. And how did they do that? Because they periodically add some heater. I mean, it's not heater. It's only it's some metal that can be coupled with some of the absorptive wavelengths, and because the heaters are arranged periodically, so when the absorptive wavelength comes in, it will heat the metals, and then it will affect the non-absorptive's coupling effect. That means the weight is added on the non-absorptive wavelengths, while the absorptive wavelength is used to tune the weight. This sounds trivial, right? So they have a lot of noise or error analysis on that, and they are trying to use some data science technique to prove that this thing is not as noisy as it looks like, but they only tested on two intensity summation. That's crazy, right? Because in reality you may have a huge input vectors lambda 1, lambda 2, and so many, like this vector is definitely not 2, right? But they only test the 2 wavelengths control of the weight. So they say that the lambda 1 and lambda 2, their effect is to directly add, their effect is gonna directly add up, but in reality you must have more, like tens of dozens of lambda, and their effect will be too noisy to be measured. You can see for 2 lambda it is already very noisy like this. Also another thing I want to say is this paper didn't apply their technique to any neural network, so even though they claim the dimension is enough for the neural network vector matrix multiplication, they didn't use that. They just say the dimension is enough. Yeah, in theory it's enough, and they do a lot of noise calibration. Well, right, and so the utility is still pending for this work. That's it. I think I'm also doing this field research, but my research is mostly on diffractive optics rather than on-chip photonics. But this has always been interesting to me, and for the job positions, they also, this research field also provides a lot of job positions. But if you have some different or interesting ideas about this field, I'm very open to discuss, and that's it. I think both two paper proves that they have some novelty, but I prefer the first. I prefer this paper more, and second paper, yeah. I would say overall this field doesn't looks too promising to me. That's it. Yeah.